Okay, let's have a talk about mapping of reads. And read mapping or mapping of reads. This is the setting we are faced with, you could say. We have sequenced some genome, so we have lots of reads, and presumably these are short reads. These are short reads, right? That's what we are focusing on, Illumina type of reads. So it's also often read pairs, but reads are short. We also have a similar genome that we have already sequenced, or someone else has sequenced it and assembled it. It doesn't have to be a whole genome. It can only be parts of it. It could very well be our own assembled contigs, right? We have used the reads to assemble contigs, and now we want to map the reads to those assembled contigs. But just as often, this genome sequence that we can imagine here comes from some other source, right? Before we did our sequencing. So typically this can be, we have sequenced a strain of some bacterial species, and this is the genome of some other strain of the same species, right? So it has to be very similar to the one we just sequenced, otherwise this is pointless. And now we want to align the reads to this reference, right? So this is what we call a reference, this already existing genome sequence, right? And we want to see where do the reads match, of course, because that means this genome is now sequence is similar or identical to this one in those regions. We also want to see regions in the reference where we have no matches. That's also gives us some information, and we can collect reads that did not match the reference. So it could look like this. We have the reference, we map the reads, as we say, or align them. So I indicate here these reads map at these regions, right? They are identical to these regions of the reference. And here we have another, but notice there is a region in the middle here with no reads map. If this is something we observe, then we can say, okay, this region here is in the reference, but this is not in our new sequence genome. Because if it was, there should be some reads here, right? Matching this part as well. But since there are no reads, we can sort of conclude that this region is no longer, this is not part of our new genome. And also the other way around, we can have a lot of some reads left over here, you could say, that did not match anything on the reference. And this could be from some new region in our recently sequenced genome, right? This could, of course, also be due to errors in the reads. So we cannot really conclude right away that all these reads come from some new region, but we have to dig a little bit further then to say that. But at least if we have a lot of reads left over here, we can do something to them. And we will also actually see later in this course that we do read mapping in order to sort of discard reads that are contaminants. And then these are the reads we are interested in, really. The reads that map to some contaminating organism, we throw away. And these are the reads we keep, you could say. So yeah, we will come back to that when we talk about metagenomes. So why do we do read mapping? Well, there are many different reasons for it, and we already saw a little bit. We can actually we can compute the actual read coverage, and that's very frequently done. And then you map your reads back to your own contigs, right? You first make contigs by a sequence assembly, and then you map your reads to these contigs to compute the actual read coverage. This can be used to evaluate the contigs, really, to see if you have sort of normal coverage because all the contigs, at least when you do single genome sequencing, in principle, all the contigs should have more or less the same coverage, right? We know that coverage varies a little bit due to this Poisson distribution, but not super much. So actually the QoST software that we have used in this course can also be told, you could say, to do this. If you feed the reads, the raw reads, to the Quast software. There are some options for that. The Quast will also do read mapping and report the coverage of the different contigs. But we haven't done that because it's very time consuming. You can also use this to understand what is wrong with the reads that doesn't map, right? And wrong in it doesn't have to be, it could be of course due to errors, right? But it could also be some good reasons for it. So wrong in quotes like this, right? Okay, so when we do some mapping to a reference genome, so this was for our assembled contigs, right? If we have a different reference genome, why do we do read mapping here? Well, you could actually look upon it as an alternative to sequence assembly. Because if this reference is very, very similar to your recently sequenced genome, you can actually reconstruct the whole genome by only mapping to that reference and see where you have the tiny differences, and the rest is identical, right? And this is frequently done for eukaryotes because different sort of individuals, you can say, in the species, eukaryote species, will be extremely similar to each other when it comes to genome sequence. The two human beings are almost identical, right? So all the reads from one person will map to the genome of another person. It's only a matter of tiny, tiny differences. For bacteria, it's not that simple. You can also use it to find SNPs or other variants. We will have a short look at that in this course. So again, this is more popular for eukaryotes, I would say, but it's also possible for prokaryotes. And of course, we can discard reads from contaminants. That's what I mentioned in the previous slide. We are actually interested in the reads that don't map to some genome, if this genome represents a contaminating organism. And this is only really valid for metagenomes. We will come back to that. Alignments, that's what we are actually talking about now, aligning the reads to the reference, right? And we have from introductory bioinformatics learned a lot about sequence alignment, and you may remember the Needleman-Wunsch and Smith-Waterman algorithms, which is sort of the optimal algorithms in a sense for aligning two sequences. They have no heuristics. They guarantee you to find the best possible alignment. We also learned about BLAST, which is a heuristic algorithm, because these ways of aligning, they are optimal in the sense of finding the best solution, but they are really slow. So BLAST is trying to speed things up by cutting some corners. No longer guarantees optimal, but it's close enough for us to be satisfied, right? So this is a tool we use for searching in a database of many, many sequences. So what we are doing now, we could in principle use these methods, both these optimal algorithms and also BLAST actually. There is no reason it will not work. It's just a matter of time and memory usage, computing resources, you could say. So aligning reads to some reference sequence, the problems are running time and memory. So it's not sort of a qualitatively different problem. It could be solved by the old methods, you could say, but it will take a lot of time. Even BLAST will make is far from optimized for doing this type of jobs. Because what are we looking for now? We want to align a huge number of short sequences, our reads, to one or a very few very long sequences, the reference. This is typically the setting now. And this is very different from what we use BLAST for, right? You typically use BLAST if you have sort of one gene or a protein, and then you want to search for similar genes and proteins in a database. So the database consists of many sequences, not one long, and the sequence that you have one sequence that you search with, not a million like we have here. So it's a sort of a different type of problem. And for this reason, specific algorithms have been developed, of course, for this special problem. So let's have a look at the Burrows-Wheeler transform idea now, which is one way of solving this, and a popular way, I would say. So that's the focus of this Burrows-Wheeler transform and the FM index. Why is this a smart approach to solving this particular problem? And first of all, we can see it as a two-step procedure like this. First, we create an index, which is actually a sort of a database, and we create this from the long reference sequence. Right? So that's the first step. It should try to use not too much memory, right? Because these references are typically quite big, the genomes, right? Millions and even billions if you go to the eukaryotes of base pairs. It should also be fast to see if a read matches the reference. It doesn't matter if this step 1 is a little bit slow, as long as the step 2 here is fast, because this is where we spend most of the time, right? Looking up if a single read matches the reference, because there are so many reads. So each lookup here must be fast. We have only one reference, so this can be slow, right? Step 1 can take some time. Prepare the database. But once the database has been prepared, it must be super fast to look up if a read matches somewhere in the reference, because this is going to be done over and over again millions of times. And we also have to save the result in a smart way, of course, but that's not something we focus on here now. I would like to say a few words about the big O notation, and this is something we talk briefly about in introductory bioinformatics as well, so you should actually have heard about this before, but let me just briefly repeat what we are talking about. Algorithms are characterized by how the running time grows as the size of the problem grows. So let's say we have the size of a problem denoted as x, and then the running time is a function of this, right? F of x. So how will f of x grow when x grows? That's what this big O notation tries to tell us. And then we typically say that some running time of an algorithm is big O of some function g of x. If there are some criteria, first of all, there is a fixed lower threshold for problem size x, and we don't care how it looks like below this value. There is also a scaling factor, and then once these are given, we have that the actual running time is always smaller than or equal to this function OK multiplied with this constant. You have this possibility of having a constant that you multiply with here, so it doesn't have to be exactly limited by this function, but this function times some constant. So notice what we are actually saying here. The running time, the values here, should always be smaller than the values here, multiplied with a constant. And then this function here tells us how this grows, right? As you increase x. And this only applies when x is larger than this minimum x0. So x0 is a sort of a lower problem size where this is of interest, because we are really interested in the bigger problem sizes. Right? I mean, for small problems, this is not really an issue at all, right? Small problems are always small. It's for big problems, right? Big x values that this becomes interesting. So we can actually think of it like this. Here I have a ordinary coordinate system with x along this axis here, and up here we have the function value, right? So you can imagine this is our running time function, right? It's a little bit, it's not an exact mathematical function. This is how long time it takes to solve some problem, right? Using some algorithm. So if the problem size is here, it takes this much time, right? So up here is sort of time, you could say, running time. So if you're here, it takes this much time to solve the problem. And if you increase the size of the problem out here, It takes a little bit longer time to solve this problem, right? But it goes a little bit like this. And then we can imagine we have a very smooth, nice mathematical function, g of x, that looks like this. And now we can say that f of x is big O g of x. And why can we say that? Because there is no a threshold here, x0. And if we go for x's larger than this, right? On the right-hand side of this x0, we can see that the blue curve is always smaller than or equal to the red curve. It's limited by this g of x function, we say. So it's not exactly the same. It's always a little bit less, but we should now try to, if we can find a function, a smooth and nice mathematical function g of x, which is growing at the same rate as the blue one, we have found the limiting function for f, and this is how approximately the running time grows as the problem size increases here. So you can see that it starts to level off, right? Because it has a negative curvation here. Yeah. There are many types of limiting function, of course. We will see some now. I should also say that the symbol x is not the typical symbol we use here. I used it here, but we typically have other symbols for the problem size. But it's just to replace x with that symbol, and it's the same mathematical reasoning. So let's have a look at a short example, which is exactly the problem we are looking at now. Find how many places a read R matches in a genome of length G. And here is our algorithm. This is the sort of the brute force algorithm. Match R at position 1 of the genome. Start at the first positions of the genome sequence, right? Does the read match here? Yes or no? Then move one position to the right, match the read here. Does it match? Yes or no? And continue. Match the read at position 3, 4, 5, up to capital G, right? So this requires this many operations. One sort of matching at each position. Actually, it requires R times G, right? Because you have to match every symbol in R at this position, but G is a much bigger number than R, right? So we can see that it requires G matching operations. So the size of the problem is G, right? What if we now have a much bigger genome? If we double the size of the problem, so going from this to 2G, then of course we need 2 times as many operations, simply because there are double the number of positions. And this means that the running time for 2 times G is approximately 2 times the running time for 1 time G, right? So we say that the limiting function is actually this linear function. Function of G is G itself. So it means that we can write the running time of this algorithm of matching like this is big O of G. So it grows linearly by the size of the genome. So we would actually, if I'm trying to, it's actually a straight line like this, right? Where we now have, so this is my geo. Oops, it's not so easy to write with this mouse here. This is now our GOX, right? Or actually GOG. That's the, we used capital G now for the problem size. So this one is the G axis, right? Not the X axis anymore. But this is how it grows, right? Double the size of the genome, double the amount of operations you need. 10 times as big genome, you need 10 times as many operations. There are some commonly seen running times that and all of them are sort of simple mathematical functions, right? That's the idea here of finding a simple G that says something about how this running time grows. The best running time you can ever have is this one, 001, and that's the big red line down here. It means that regardless of how you increase the problem size, it takes the same amount of time each time. Now, this is almost too good to believe, right? It means that, but this is the case in some problems. For instance, if you have, I'm not sure, if you have a sorted list of numbers, find the smallest number, and that's always the first number, right? If it's sorted. So then it's big O of 1. It takes the same time each time, and it doesn't matter how many numbers you have, because looking up the smallest one is always the first. So this is in particularly nice situation, right? Then you have the yellow curve, which means it's logarithmic. So it's getting flatter and flatter. So it grows pretty fast in the beginning, but that's not. We are not too concerned about that, because remember here the problem size is small. So it doesn't matter if it grows fast here, because the problem is small anyway, and the running time for a small problem is always small, you could say. It's how it grows when x get big. And this grows extremely nice because it grows less and less, right? Then, of course, we have the linear one that we saw in the previous slide. This one here, it's not too bad either, but double the size of the problem and you double the time it takes. That's basically what it means, right? And then you have the really the more horrible ones, the polynomial times, as we say. And this one is one of them. I think this is squared, right? X squared. So for n equals 2. And this is typically aligning two sequences with the Smith-Waterman or Needleman-Munch algorithm, has running time big O x squared. So we can see it grows more and more and more. So going from big to super big problems, it doesn't double, it's quadrupled, right? And for n bigger than 2, it's even worse. And then you have the really, really horrible problems in this world, and those grow faster than polynomial. And there are lots of them. And those we call the non-polynomial running time problems, NP problems. And the NP complete or NP hard problems, they are actually in principle insolvable by computers. Because the running time, you can solve them for tiny problem sizes, but once it starts to grow a little bit, the running time becomes so horrible, it's not really possible to solve it in any reasonable time at all. And some of them not theoretically even. But we will not dig in more into this, but just remind you how this big O notation indicates how fast the running time grows as we increase the problem size. So let's turn back to this Burrow-Wheeler transform. And what is actually the idea here? And it's not easy in the beginning to understand why this is a good idea, but I would say if you read the text by Ben Langmead that I linked to, it's a very good text for explaining this. It's the best I've ever seen. And he, not so strange perhaps, because Ben Langmead was actually the man behind the Bowtie software and was the first one to sort of to realize that this is really a good idea for read mapping. So let's see if we can understand it. And we have now a reference sequence, I call it ref, of length G, right? And think of it as the genome. We want to search through the sequence for occurrences of a short sequence R, and that's our read, right? So we want to see, do we find the read here? And also, ultimately, where does it match if it matches? But first of all, we want to just say, does this read match in this sequence or not? And even perhaps if it matches once or many times. So What we do now is we try to build an index from this reference, which is small. It shouldn't be super big because we know that computer memory is not infinite. And some of these references can be really big, right? But most importantly, we must be able to quickly find where this read matches in that long sequence. Well, a suffix, this is just a word you come across when you read this text, so I just mention it here. A suffix of length n of some sequence, doesn't matter which, is actually just the subsequence of the last n characters, right? The last n characters. And this is for any sequence, whether it's the read or the reference or whatever, right? A suffix is the last part of a sequence. So let's use this tiny little example here when we go through this illustration now. So this is our reference, which is of course very short, but it's always a good idea to have these tiny little toy examples to understand the idea. And the read is super short. And of course, in this particular case, we can immediately see where the read matches. It matches here, CAC, and it matches here, CAC. I think that's all. Yeah, but imagine this being millions, even billions, and this a few hundred characters. And we have many reads, right? Whoops. The Burroughs-Wheeler transform, what is it? First of all, add what we call a terminator symbol to the end of the reference sequence. And the dollar sign is frequently used because this symbol should not be part of the alphabet, right? It should not be G, A, G, A, C, G, T, or anything that can be confused with the alphabet. So it must be something completely different. And it must be lexicographically preceding the alphabet symbol. So it means if you sort this alphabetically, this one comes before A, C, G, and T in that sorting, right? And if usually this is sorted by the ASCII values that we have seen before when we talked about quality, sequence qualities. It's sorted by the ASCII values, and then dollar is before these capital letters. The idea is very simple now at the beginning. Arrange all the rotations of the reference into a G times G matrix. Sort all rows in ascending order. That means alphabetical order here. The last column you then have is the Burroughs-Wheeler transform of the reference. So what is actually first here? Arrange all rotations. What is meant by this? Here we can see that this is the original reference sequence, right? Like it is here. What is meant by a rotation? A rotation means you take the first symbol and you just place it at the end, and then you shift everything one position to the left. And then you have this one, right? The second one here. This is the first rotation. And then you do the same again. You take the first symbol here, move it to the end of this one, and move everything one position to the left again. Then you end up with this one, right? And then you continue doing this and over and over and over again. And you can see that there will be one new sequence here now for each position in the original reference. So that's why it's capital G rotations. Then we sort these rows here in alphabetical order. So it's actually the same rows, but they have just been given a different ordering. And then, of course, the one with the dollar, starting with the dollar, comes first, right? Because of this requirement up here. And then, of course, all the rows starting with an A, and of those, A dollar is the first, and then AA, right? And so on. So these are, and then you have all the rows starting with a C, and then all those with a G and T and so on, right? And this is what we call the Burroughs-Wheeler matrix, the whole matrix, you can say, with all the symbols. But the Burroughs-Wheeler transform is actually this last column here. Only the last column. And remember now, since we have capital G letters in this reference, we will have capital G rows. So the Burroughs-Wheeler transform is actually another sequence, you could say, of the same length of the original, but the symbols have been rearranged in some mystical ordering. And why on earth was this a smart thing to do? It's impossible to see it at this point, but hopefully it will become clear. So from this Burroughs-Wheeler matrix, what we are now storing, you could say, or bringing with us into the next slide is this last column, but also the first column here. The first column here. And we forget about everything in between. So this is what we call the FL. First and last column of this Burroughs-Wheeler matrix. Yeah, this arrow is, we will explain it. The output from the Burroughs-Wheeler transformation is the first and last column of this Burroughs-Wheeler matrix, you could say. The L column, that's actually the Burroughs-Wheeler transform, right? And look at the F column. It has a very simple structure. Can you see that? It starts with the dollar. Then we have all the A's. All the A's in our reference sequence are now coming here. Then all the C's. Then all the G's. And then all the T's. Right? Go back to the previous slide and see why it has to be like this. It has to do with this sorting in alphabetical order, right? So actually the information we have in this column here is only how many A's, C's, G's, and T's did we have in our reference. That's all the information there is, actually. To use this for anything, we also need to compute ranks, and that's what you see in this third column here. What do we mean by rank? Well, we simply go through the Burroughs-Wheeler transform here now, the L column, and we sort of count how many times we see each symbol. So A, this is the first time we see an A. So this is rank 1, right? For A's. This is the first occurrence of a C. It has also rank 1. But here we have another C. So this gets then rank 2, right? This is a second C, right? This is the first G. It has rank 1. And then we have a C again. Now the rank is 3 because we have already seen 2 C's before, right? And so on and so on. So that's the explanation for these values here. You simply numerate the symbols from top to bottom. So this is number A number 1, A number 2, and A number 3 here, right? If you now look at the rank in the F column in the same way, you will find mysteriously almost, but not so mysteriously at all if you start thinking about it, the character with rank X in L is exactly the same character with rank X in F. So it means that this particular A that has rank rank 1 here is exactly the same A that has rank 1 here. So this A and this A is the same A from the reference. And this one, this A here, is exactly the same A as this one here. Right? And this applies to all symbols. Go back to the previous slide to reveal why this is the case. The inverse Burroughs-Wheeler transform. So given this information here, the FL and the ranks, we can inverse the transform. And how can we do that? We can rebuild the original reference backwards from this information here. It just shows that there is a sort of simple relation between the original reference sequence and the sequence we have in this column here now. Even if it looks very different from the original one, right? If you look at the symbols, A, C, C, G, C, C, T, it doesn't look at all like this one if you read this one from the beginning. But there is a simple relationship between them. And this is how you can sort of transform from this one back to this one. Start at row 1 here. And let me try to do this actually now. I think I will, let me see, is it possible to have a different color here? Yeah. Start at position 1, at row 1. The L symbol precedes the F symbol in ref. So we start with the first symbol here, right? So my reference should end with this one. And then it's preceded by this A. So I start building it backwards. Then we use the rank of this A. It's not, rank 1, right? And then we go to this F column here and look up A number 1. And that's this one. And then we can see this is now preceded by a C. And this is C number 1. So we go back to the F column and look up C number 1. Here it is. This is preceded by a T. And this T has rank number 2. And then we go into the F column again and look up T number 2. There it is. This is preceded by an A. Can you see now that this turns out to be exactly the reference? We build it backwards. And then we can go on like this, right? So this was A number 7, right? And then we go in and find A number 7. 1, 2, 3, 4, 5, 6. This is the one. And it's preceded by another A. Yeah. And so on. And we build this gradually up like this. And we get exactly the same reference as we started out with. So it means that this L sequence here has a sort of very close relation to this one, and we can go back and forth between them. There is a algorithm for turning one into the other. So this inversion property is the key to using it as an index, really. So this FL, these two columns and the ranks is what we call the FM index. This is actually the database in a sense, but it's a little bit more to it than this. Let's go on and see. Search for a read in the reference now with this FM index. How can we do that? So let's see if we can find the number of occurrences of this read here, CAC. And let me go back to this, and I think I will use a red pen. How can we find if this read here is found in our reference sequence? How do we proceed? Well, we start by the last symbol, the suffix of length 1. And then we go into the F column here and see where do we have the C's. And they are found here. There are some C's in this reference. Right? This reference sequence contains some C's, 5 of them actually. And then we look at the preceding symbol, right? We see that now we look at the suffix of length 2, and we see that this one is preceded by an A. Okay, how do we see, where do we see a C preceded by an A? Well, we see it here and here. Remember that the symbol to the right of the F symbol is the one that is preceding it we saw in the previous slide, right? So we can actually say there are 2 occurrences of AC in this. in this genome. There were 5 occurrences of only C, but 2 occurrences of AC in this reference of ours. And then we look at the suffix of length 3, the preceding symbol here, and now we need to use this ranks, right? Because this A had rank 4 and this A had rank 5. So now we need to go back into the F here and find A number 1, 2, 3, 4 here and 5 here, right? To look at those preceding symbols. And both of them have a C actually. So the read CAC occurs 2 times in our reference. And now we're done. We have looked up the read now. So this is how we can use this information to reveal this. Another example here, TCT. Let me change the color of my pen. So again, we start at the suffix of length 1. We go into the F column and see, okay, here we have T's. There are T's in this reference. There are 3 occurrences of T. And then we look at the suffix of length 2, T preceded by C. Okay, 1 occurrence only of this. And this C has rank 5. So in order now to look at the next symbol upstream, you could say, of the C, the suffix of length 3, we now need to jump to the C number 5, right? And that's 1, 2, 3, 4, 5 here. This C here. And how many of these are preceded by T? None of them, right? There is only one, and it's preceded by an A. So we can say that, okay, this read here is not found in our reference. There is no TCT in our reference. So this works, but it's still sort of slow because scanning for the ranks is still the running time of that is still the same as the running time of or it grows by linearly by the size of G, right? Because for each, remember we sort of looked up the C section in this column, and then we looked for the preceding symbols in that C section and in the A section and in the T. This depends on the symbols, of course, but I mean, if you double the size of the genome, you will also pretty much double the size of these sections, right? So as long as you have to scan through a whole section like this, it's still running time big O of capital G here. It still grows linearly. So how can we fix this actually to make it faster? Well, we can use a trick like this. We can save time and using more memory though by what we call the rank all matrix, and that's what you see out here in the gray now. So instead of having a single column with ranks, we now have a matrix with 1 column for each symbol, A, C, G, and T in our alphabet. So that's why we use more memory, but this makes the lookup much faster. Let's see how. Well, when we looked up the read, we looked up the last symbol in the read, which was a C, right? And then we found where do we find C in this column here. So let me actually go back to this pen again. And this C section, you could call it, is actually from row number 10 to row number 14 in this index. And how do we actually know these 2 numbers here, 10 and 14? Where do we know them from? Remember the simple structure of this column. If you know how many A's you have, in this case 9, then I know that the first C, of course we have the dollar, right? So it's 1, 2, 3, 4, 5, 6. It's 8 A's, right? $1, 8 A's, which is together 9. Then the first symbol, the first C must be in element number 10. And if I know how many C's I have, then I know that the last C will be in 9 plus the number of C's, which is 14. So you don't really need to store this F column. Can you see that? You only need to store how many times do I see a dollar? It's always once. How many times do I see an A? How many times do I see C's, G's, and T's in our reference? 4 integers. That's all you need. Okay, so we know since the last symbol in our read was a C, we are now sort of focusing on these rows here, row 10 and row 14. And then the preceding symbol to the C in our read was an A, right? We know that it ended like this, C, A. That's how the read ended. Then we go into the A column now, focus only on that. And then we look up the value in row 14 and in that column. So it means this number here is actually 5. And we look up in row number 10 minus 1. So we go sort of one step up and look up this number here in that column. Right? And this is just a pure lookup. You don't need to sort of search through here to look for anything. So it doesn't matter if there are, in this case, it's 5 C's, but it could be 5 million C's here, right? It would be just as fast to look up these two numbers because we know exactly which row to go into, which two rows. And then the A ranks that we are now interested in are always these. Always these, 4 and 5. So instead of having this scan here through this section, we now need only 2 lookups to find these two numbers. And from these two numbers, we have all the ranks of A that we are going to need, 4 and 5, right? And go to the previous slide to see that this is actually correct. And this is always correct, it turns out. So instead of scanning for through the whole reference, or actually all the C's in the reference, we need 2 lookups. This is super much faster, right? So this is a really big, smart idea. Saves us a lot of time. The problem is, though, it consumes more memory because now we have to store 4 columns here instead of 1. So there is sort of an intermediate solution here that is used in practice. So if we go 2 slides ago, we used little memory, but we had to use this slow scan to find the ranks. But in the last slide, we used more memory to make the extreme fast lookup of the ranks. And now we give and take a little bit in both directions. So we don't actually store all the ranks in this rank all matrix. We only store some checkpoint ranks, as we call them. So you can see every nth rank sort of in are stored, and the rest are not stored. So we save a lot of memory. This matrix becomes smaller because we can throw away these rows. But still, we need to look up the ranks in these rows. But then we can do the search, right? Because now the number of, or the length of the section we have to search through is the same each time, right? It doesn't depend on how long the reference is. The length of the reference will now only affect the number of checkpoints, but not the size between each checkpoint. That's fixed, right? So this is now big O of 1. It's a constant time, right, to look up in between 2 checkpoints. Doesn't matter how many checkpoints you have. If you're going to look up between 2 checkpoints, it takes the same time each time you try to do it. So as a summary, we can say that the memory how much memory do we need? We need to store the L, right? So it can't be less than the genome sequence that we started out with. But this can also be stored very efficiently when we have DNA, at least, because we have 4 symbols. So we can use a 2-bit coding to store these 4 symbols. We don't need to store the actual text. And then we store the number of A, C, G, and T, right? That's the F column, right? We don't really need that F column at all, only these 4 numbers. And also the $, which is always 1. So 4 integers, really. And then we need to store those checkpoint ranks that we saw in the previous slide. So that will also consume some memory. But this is not bad, right? And the running time, if R is the read has length L, capital L, then the range of the last character is given by here, right? We immediately find where this if we saw if the last character was a C, we know exactly where the C section starts and ends in the F, right? And then the range of the last character is found by a constant lookup in rank all. I mean big O of 1, right? And then you have the rank of the second last character, right? And in order to find the rank of the third last character, it's again a lookup of order 1, or constant running time. And this means that you have to do this for the length of the read. For each symbol in the read, you have to do this, right? Which means the running time for the whole looking up of a read is big O of read length. And this is almost too good to be true, isn't it? It actually tells us that the search time depends on the read length, not on the reference. Isn't that amazing? I mean, if you have a database consisting of trillions of bases, it doesn't matter. Finding a read in there takes the same time each time you look up. That's almost magical. But this is actually the case. So the Bowtie software was built around this idea. And the first step you will see when we are going to use it in practice, there is sort of a 2-step procedure. First, building the index, and that's where we build use the Burroughs-Wheeler transform to build this FM index. So that takes some time, right? But once this is done, you do the searching with the read pairs against this index, and then we have this super fast lookup. We have only considered exact matches in this example here. In reality, the Bowtie software and all other softwares will also allow for some small mismatches, but not many. And this would, if you should allow many mismatches, you need to sort of extend the search, and you lose all the gain by doing this Burroughs-Wheeler transform. But on the other hand, we are not interested in many mismatches because reads should match more or less perfectly. And if it's a lot of mismatches, it's probably due to sequencing error anyway. So then this read is just set aside as not matching, right? So you can extend this, but then the running time becomes slower, of course. There is also an upper and lower insert side because when matching read pairs, we know that the read pairs should match somewhere in the same region, right? So you also have, we also should specify to Bowtie what is the minimum and maximum distance between where 2 reads in a read pair can match. Right? It's not like it's used very sort of brutally, but it's used when reporting how the reads map. Because in the read pairs, if the reads map concordantly, it means that they map within the insert sizes. But they can also map what is called discordantly, meaning that both reads map, but too far away from each other, really. But but both will map. But this is sort of a part of the output, so you can see if the reads are mapped where they should actually map, right? But the total number of reads mapped is always reported anyway, and this is most often what we are interested in. And the output from this is a SAM file, and I will not talk about SAM files here now, but we will see some SAM files in exercise or in the examples. And all the softwares that do this read mapping, they typically output SAM files, or at least that's an option. So it's not only this bow tie doing that. There are other softwares using also the Burrows-Wheeler transform doing read mapping. There's one called BWA, which is very popular. You will likely come across. And we will also see some other software later in this course that also uses the Burrows-Wheeler transform, but in a slightly different way. So this idea of Burrows-Wheeler is something that is used quite a lot in bioinformatics, actually. Okay, let's run the bow tie to do some read mapping and look how it outputs stuff. So here, first of all, I have logged into RStudio and also logged into Orion, with RStudio, and also logged into Orion with my terminal window. I always have these two gates into Orion. And you can see here I have made a shell script by just copying this code in this gray part here and also the gray part here. The first one is for building the index. The second one is for doing the read mapping. So I pasted both into the same script. So you can see down here, everything down here is the first part, building the index, right? And then the second part here is the mapping of the reads. And I've saved this in a file called shell script bowtie.sh in a module 5 folder. So if I go to my my terminal window, I can see there is a module 5 folder here. Let me move down to it and list the oops, I managed to module, and then it fills in as long as it's, because I also have some other module numbers, right? So I need to type 5 here. Yeah, then it's correctly typed. Let's have a look at the content. There is only one file inside here, and that's the script. Yeah. So now I can, in principle, run this script by S-batching it to the Slurm. But I will do, before I do that, I would now like to comment out the last part here so that we only do the first part, building the index. You don't have to do this, but I will do this now just to illustrate things. So I just highlight the code in the second part here that I don't want to run. And then I go to the code menu and choose comment. And then you can see RStudio will put some comments hashtag in front of all lines. So these are now commented out and not executed. I must remember to save my shell script file now. So only the first part will be executed now. Let's try to run it. S-batch. Like this, and I use my tab button. There it goes. And let's see if I can read the queue here, but I guess this was not seen in the queue, so either it has crashed or it's already done. Let's refresh the files window here. We can see the log file here, right? It always appears a log file, and this time I specified this name for the log file, so I can see. So we can always have a look into the log file, and we can see it doesn't look like there was some error. You can see it's a lot of output in this log file. And we don't need to understand this. It's usually a good idea to just scroll down to the end of it. It has almost 3,000 lines. And I can't see no error message here. It just said it finished in 2 seconds. So this was really quick, making this index. Of course, the genome we use now is not super big, so that's probably the reason. So this was very quickly done. Uh, where is actually the result? There is no result here, and that's not so strange because the index, if you go to the command line here, how does it look like? Yeah, this is the bow tie container, right? All the way down here. We specify the singularity and the bow tie container. Then we say bow tie build, which is the command that we use now. And here are the options. Yeah, we specify the number of threads to use. Which reference do we have? That's defined up here, right? And the index to create. That's the last input. $index. And this is here. So we make an index called bowtie_index in the outdir folder. And what is the outdir folder? And that's specified on the line above. It's on the scratch disk, right? Scratch/bowtie2. So we should now actually move to the scratch disk to have a look at how things are there. So we do like this: cd scratch, jump to my scratch disk. Now I'm on the scratch disk. And if you don't believe me, here it is: /mnt/scratch/my username. What is found in this? Only a folder called bowtie2, right? Because here we actually created it, right? You can read about this in the text. So we actually created under Scratch a new folder called bowtie2. And there it is. So let's jump down to this one, jump into it. And what's inside here? Yeah, a number of files. Let me just output it in a slightly different way with the long format. So this is how it should look like. There should be 6 files. And notice all of them have the same prefix, bowtie2_index, which is exactly the text we specified here, right? But there are 6 files with different suffixes. And that's what bowtie always creates. So the index is actually scattered across 6 different files. And these files are binary files, so don't try to look into them. It's impossible to, it's not text files. These are binary files. So this is the output from building the index. So now let's take this comment away and zap like that and rerun. And of course, we could now comment out this building of the index here because we don't need to build it again, right? It's silly. We have already made it, so why should we make it again? But it took 2 seconds, right? It's extremely fast, so it doesn't really matter if we build it again. It will just overwrite the existing files with new files which are exactly identical to the ones we overwrite. So it's not really a big point in commenting it out, but in principle we could have done that. In some other cases we would have done it because building the index can be, if the genome is really big, this takes some time. But first let me try to rerun my script, and then I have to jump back to my home folder, right? Away from the scratch and back to my home, and now down to the module 5. I keep typing this wrong. Module 5. There. Now I'm back at the module 5 folder. We can see the log file. We can actually delete that log file now, right? We don't want to look into it again, so I delete it. And I have to remember to save my script. You can see it's red up here, so it hasn't been saved. So if I sbatch now, I get the old version of the script started again. But now it's been saved. And then I use my up arrow to just repeat previous commands, because somewhere back here I had this command, sbatch. There it goes again. And this time it will take some longer, right? So now it started, and now the index has been rebuilt. I suppose. We can actually have a look at the time here. When we looked at these files previously, this is when they were created at 1319. If I now go back to the scratch disk, scratch like this, I go down to the bowtie folder and I run ls-l again. Notice that these are now not the same files we saw previously, because these are created at 6 minutes later, right? So we can see that it has been recreated, these files. And we can also see there a new file has appeared now, a SAM file, right? Because that's what we specified here. The SAM, the output that we end up with after read mapping is always a SAM file. Well, not always, but in this case it is. Bowtie outputs a SAM file. So here we have the command, right, for running bowtie. This is the container again, and then we run not bowtie build this time, but just bowtie for read mapping. And we have some options here. And here is the insert sizes, right? Should be somewhere between 0 and 1000 bases. Here we indicate which index, exactly the same we built up here. The two FASTQ files with reads that we want to map. And then we tell bowtie to output things in SAM format in this file. And SAM file is exactly this one. And this file is created once read mapping is started, but it will be filled gradually. So notice here how big it is at this time, 1326. The file existed and it has this many, this big. We can actually, let me show you. If you add H for sort of human visibility, we can get sizes in a more readable format. So now it's 893 megabytes, right? While up here it was, this is it was 98 megabytes here. So it has grown a lot, right, in 2 minutes. This was at 1326. Now a new version of the file at 1328. So this file grows all the time, because what is now being done, bowtie takes all the reads and map them to this index, right? To see if they are matching somewhere in that genome. And for each read, new results appear, right, in this SAM file. That's why this SAM file is growing and growing and growing, as long as the read mapping is going on. So let's see, is it still growing? Let me run this again. No, it stopped growing, which probably means it's done, right? So now I can just look at the queue again. Yeah, now the bowtie shell script is done. So we are finished. And now I can just sort of jump back to my home folder again and down into the module 5 folder here. So now we have a new log file, of course. If I refresh here, we have the new log file. Yeah. And let me scroll to the bottom of this log file now, because you can see that these last lines here comes from the read mapping. Everything down to here is from building the index, but the last few lines comes from the read mapping. And it's first it says it's 595,000 blah 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 reads, and this number we recognize. We have inspected these FASTQ files many times now, so we should recognize this. Almost 600,000 read pairs. It says reads, but it's actually read pairs, right? And it says 100% were paired, yes. Of these, 92% align concordantly exactly one time. And this is the number of read pairs that matches the genome within the insert sizes we specified. A few reads match multiple times. Yeah, that's interesting because that indicates some repeated region, doesn't it? And like 5% did not align concordantly, right? So from these that did not align concordantly, a fraction of them aligned but discordantly, which means the read pair, both reads in the pair match, but further away from each other than they should according to the insert sizes. We specified somewhere between 0 and 1,000 bases, right? The insert sizes. Didn't we? Yeah. Yeah, here we said max insert size 0. No, minimum insert size 0, max is 1,000. So the distance between where the reads match should be somewhere from 0 to 1,000. And some matches further away than 1,000. Yeah. But actually, what we are basically interested in is this last one. 98.74% of the reads align. And that's because, of course, because these reads are from this actual genome. The reference genome we used in this case was actually the genome that we sequenced. So in principle, 100% of the reads should match here. But of course, since some reads have errors in them, many errors also, they don't match. So we must expect to lose some. And here we lose like 1%. And that's good, I would say. So close to 99% of the reads match the genome. And now we should work further on this SAM file that we saw in the Scratch folder. Let's have a look at how we can learn how to read the help text for a software. So now we have just used the bowtie software to map reads to some genome. And here we can see the command line that we used. First of all, we have the singularity and then exec for executing a singularity container. Then, of course, the name of the container, which is pretty long. And here is the command that we actually execute, bowtie. And it continues on the next line here with some options and blah, blah, blah. How do we know what to put here? And that's what we are going to investigate now. So, first of all, let me just copy this line here so that I can actually run bowtie without this long list of options. So let me make this window a little bit wider. I just right click with my mouse here. That's paste in terminal. And then the only option I now add is -h for help. And then return. And it's not like all software tools have -h for help. I just guess this now. Many have, but not all have. So you just have to try it. You might sometimes need to type -help. I mean the word, not only the H. And sometimes you need 2 minuses as well. Yeah, but try -h first and see what happens. And usually, if you don't write anything, just the name of the tool and no option and no other input, you will also be taken to the help text. So you can see this help text here is pretty long. And it lists a number of options. But the very first we should do when we are new to a software, the very first thing we will do is to scroll to the top of this text and look for this one here, usage. Here it's described how to use this software tool. And that's the line here. So let's see if we can understand what it says here now. First, you must type bowtie2. That's the sort of the command to actually start the program. So there's no doubt about that here now, right? Then a space, and then we can have options. And notice there's these brackets here, so it means that this is something we can do if we want to, or we can just disregard this, right? Because options are optional. It's in the name of it, right? But we can have options, and if we want to have options, they should be placed here. The first thing you do after you type bow tie. So this line here now is important for telling you in which order you should type things on the command line. So bow tie, then a space, and then options, as many and as few as you like. Then you must specify the index. And this is, it says -x, space, and then something here. And if you see it's explained right under here, what is meant by this here, it's this one, index file name prefix, right? Minus the trailing blah blah blah, right? And if you have inspected the index we got from Bowtie, see my previous video, you will understand what this means. It's the name of the index, right? Okay, so that's the sort of third input. Then the fourth input is this, starts with this curly brace and ends with this right hand curly brace here. This is the fourth input. And what is this? It's either this one or this vertical bar means an or, right? Or this one, or this one, or this one. But only one of them, right? Not all of them, since it's an or here. So if you have paired end reads, you write it like this: -1 and then the R1 file, -2 R2 file. And this is explained here, right? M1 file with number 1 mates, M2 file with number 2 mates. So that's if you have paired end reads, you choose this one. If you have unpaired reads, right? Unpaired reads, then you do it like this: -U R only. And that's sometimes we have unpaired reads because perhaps we did some pre-processing of our reads, right? And that leaves us with some unpaired reads, or for some other reason. It could be we only have single reads from the beginning, right? Then we have to choose this option here. If it's not a pair of files, but just single FASTQ file. We can also have paired end reads in an interleaved format, which is not that common. It means that instead of having the R1 and R2 reads in two separate files, they are merged into one file where you have first the R1 read and then the R2 corresponding R2 read, and then the next R1 read and then its corresponding R2. So they are sort of mixed, right? In every second read is an R1 and every second is an R2. That's interleaved format. And you can also even have input as a BAM file here. We will not dig into this, but we can see there are different ways of specifying the input, the query, right? What do you want to map? And then the last chunk of input, you can say, or on the command line is this one, specifying the SAM file. And notice this is also optional. Having these brackets. So if you don't specify anything, the output will be to the screen, which is of course horrible, but possible. So usually we use this. So if we now go back to our own command line, we will see that it follows exactly this pattern. Yeah, first we start with bow tie 2, then a space here, then it continues. One option here, next option here, third option here, fourth option here, fifth option here. So we have 5 options before we specify the index. So we could have had nothing here, right? This could have been empty. You can delete this and it will still work. It will not do the same thing, but it will still work because these are options. This one, however, is not optional. This must be there. We must have an index to map against. Otherwise, you can't map, obviously, right? And then we have the input section here with our reads that we want to map. So we have chosen this format now since we have paired and reads. And then we have the output to a SAM file. So notice that this usage line here is extremely important for understanding the order of the input to this command, right? You have to start with this one and then the options. You couldn't, for instance, put this part directly after here because then it will probably crash, right? It will first have the options. However, options, the order of the options can be random. I mean, it's not like you have to specify this as the first option and so on. So inside here, you could say, if we go back to our command line, in this part of the command line, these options can be mixed in any order, but they must appear here and not back here. So we could have started by specifying the threads and ended by specifying sensitive in this section here. But it must be in this section. That's the point. Okay, we have another software here we used, Bowtie Build. We can do exactly the same thing for Bowtie Build and see. Let me copy from RStudio. We copy like this, and then I go back here and clean my screen again. Right click, Bowtie Build, and -H again to get some help text. And this was much shorter because there are very much fewer options here. But again, look for the usage. And here we see it. First Bowtie Build, then a space, and then you can have the options. And then you must specify the reference. And it says here, reference in, a comma-separated list of files with the ref sequences. Right? So you can actually have multiple files, multiple FASTA files. Right? It's typically FASTA file because it's sequences, right? So we have used one single file here, and then you must specify what do you want to call this index, right? So here it's BT2 index base. Yeah. So here you specify the folder or directory and the prefix, the first name of the index, right? And then you have all the options here, which is not very many, but some. So if we go back to so we can see we specified Bowtie Build and then one space. Whoops. It's important there is a space here before the line break. This backslash is a line break in Unix because there is no space here. All right? So if we delete the space here, there will be no space between Bowtie Build and -- threads. So we use only one option in our case, then the reference, and then the name of the index. Okay. What if we what if we don't know how to start the software at all? We are told to use some software, but we are not sure if this is the proper command. How do we know that this is the command for building a Bowtie index, right? Because we only use the Bowtie container. How do you know that this command here, Bowtie build? Well, the only really solution to that is to go and look up the the help, the manual for the software. And notice at the top of these documents I produce, I always list here the softwares we use in the module, and then I also list a link. I also have a link to the GitHub sites. And you should be familiar with Git and GitHub. It's not something I teach in this course, but this is something you come across all the time when you run software, right? On bioinformatics software. Everything is out on GitHub. And this is actually the place to start go looking for information about the software. You find the GitHub site of the software, and then you start looking. And the first thing you will see is actually the program itself and all the files you need to download in order to install the software. Luckily, we don't need that since we use the containers. But if you scroll to the bottom of this first page, it's usually some information here. And this varies, of course, a lot between different softwares. Some have a lot of information, some almost nothing. This is sort of a little bit in the middle, I would say, because there is a small sort of how to get started here. How do you obtain Bowtie getting started here, right? So it's not a full user guide, but it's a way to start. And here already we can see some examples, right? Here is some example. Aligning paired end reads, for instance, right? Here. So here we can already get a very good sort of recipe for how to start out. So we can see that there is no options here, but it's specified an index, and then you see the -1 option for specifying the R1 read and the R-2 for the R2 read. Right? So this is a sort of a very short version of it, but it's a start. And here you can see how to build an index, and then we can see how to use, we should use the command called bowtie build, right? Called bowtie-build. So this is how we discover these things. And notice again, they use this. So here we build. The input is a FASTA file. How do I know? Well, I can see it's .fa. It's usually a FASTA file. And we can see that this FASTA file is taken from some folder called example with a subfolder called reference. And there is the file, right? And now the index is put into the example folder with a subfolder called index under the name lambda virus. These things you should now understand, right? You can see the slashes and the paths that you should get used to see. This you will see all the time when you start looking into bioinformatics software. Everything is explained as command lines. Command lines, command lines, command lines in a Unix world. Let's have a look at, we are going to use another software later in this module. It's the Minimap 2 for mapping long reads instead of short reads. And we can do exactly the same here, of course, hoping that Minimap 2 also has a -h option, and yes, it has. Almost all softwares have this. And again, there is a usage at the beginning. Minimap 2, then the options. This is quite normal, right? You can see almost all softwares are built on this sort of same skeleton of. And then there is some target FASTA file, which is what we are going to map against, I suppose. It doesn't really explain what target means here. You can see this is a shorter and not so wordy help file as you saw in the Bowtie. And then the query. Query is what you want to map, right? These are the reads that you want to map. And this is what you want to map against, I suppose. So this is the sort of reference or index. It doesn't really build an index, so that's why it doesn't call it index. So Minimap 2 works in a different way. But again, we see this is how to start a command line. Then we can add options. Here must the options be, not out here, right? Then we specify what to map against, and at the end, the query file, the reads that we want to map. So if we go back to our command line here, we can see it follows this pattern. So after minimap, we have a space, then comes the options. It's all the way up here, actually. So we use some options here, then the reference, and then the reads that we want to map. And you can, of course, read now about each possible option to use here. Or you can do, as we did previously here, go to the GitHub site and start really reading about how to use this software. Here you will find much more information. And this one actually has a very good table, sort of use guide here, directly on GitHub. It's often the case, or at least there is a link to some user guide. I saw Bowtie doesn't have this user guide. At least I couldn't find it here. It might be I didn't look carefully enough. But it's a link to the publications, and this is important. When you start using software, you must add references to your reports and publications. So these are the papers you should refer to in those cases. For Minimap 2, yeah, it's a long rather, and here you can see also citation. Yeah, this is how to reference this software. Okay, so now we have started to learn a little bit more about this, and we will, you will have to try to learn this. Have a look at this help text for all the softwares we use. Spend a few minutes there and see if you can gradually start to understand what this means and all the options and what could we have done here otherwise than what we actually do. Because this is how you will survive in this world, in bioinformatics. You will need to find out these things on your own, sooner or later.